Welcome to this video on simple argument forms, which is part of the series on propositional arguments. The last video talked about simple argument forms, about conjunctions and disjunctions. This video deals with conditionals and biconditionals. If you have not watched the videos about truth relations, forming propositions expressing truth relations, and the method of loci, you should do that first. The first argument form dealing with conditionals is called Modus Ponens. In Latin, the phrase means mood that affirms. The idea is that one starts with a conditional expressing sufficiency. One affirms the antecedent, which, I take it as obvious by now, is sufficient for the consequent. Since we had the expression of sufficiency and the affirmation of the antecedent, we infer the consequent. For a memory mansion image of modus ponens, I think of poor nuns. Poor nuns for modus ponens. The form of modus ponens is intuitive enough. First, we start with our conditional expressing sufficiency. We use our p's, arrow, and cue ball to represent if p then q for our memory mansion. Next, we assert the antecedent p. Finally, we infer the consequent, q. Here's an example of modus ponens using our by now familiar rex. The next argument form is related to modus ponens. It is called modus tollens. Modus tollens is Latin for mood that denies. Again, the idea is simple enough. First, we have our conditional expressing sufficiency. Next, we deny the consequent. Recall that the consequent is necessary for the antecedent. Since the consequent is false, we infer that the antecedent is false. For our memory mansion image, I like to use a toll booth, the mode of tolling. Mode of tolling for modus tollens. Again, the form is simple enough. First, we have the assertion of the conditional. Our p's and cue ball are also here. Second, we have the denial of the consequent. Thus, we have our cue ball tied up in knots. Finally, we infer the denial of the antecedent. Just for the sake of clarity, recall that any proposition expressing sufficiency is equivalent to a proposition expressing necessity, where the antecedent and the consequent switch places and are denied. That is, the proposition if p then q is equivalent to the proposition if not q then not p. So we can have modus ponens with a conditional expressing necessity. If not q then not p is represented with our knots, cue ball, arrow, and p's. Next, we state our denial, not q. Finally, we infer the denial of p. It's functionally equivalent to the other argument. Again, here's an example of modus tollens. Hypothetical syllogism uses two conditionals expressing sufficiency to infer a third. The idea is simple. If one proposition is sufficient for a second, and the second is sufficient for the third, then we can infer that the first is sufficient for the third. It sounds a lot more confusing than it is. It's probably easy to understand when we look at the form. For a memory mansion image of hypothetical syllogism, I rely on my extensive experience with animated movies. So we have Po from Kung Fu Panda. Say, "Hi, Po." Po happens to be kicking through the air in front of a window sill. Hi, Po sill for hypothetical syllogism. The form of hypothetical syllogism is pretty straightforward. First, we state our first conditional, if p then q. Well, so far so good. The second step, we state our second conditional, if q then r. Notice something. The consequent of the first conditional is the antecedent for the second. This is our linking condition. At this point, we have introduced a new letter, R. For a memory mansion image of R, I imagine a pirate saying R. So we have our cue ball, arrow, and pirate. Q, arrow, R for if Q then R. Finally, we infer a third conditional composed of the antecedent of the first and the consequent of the second. P's, arrow, R for if P then R. Hypothetical syllogism works just as well with necessity as it does for sufficiency. First, we have a conditional expressing necessity from P to Q. Next, we have a second conditional expressing necessity from Q to R. So we infer a conditional expressing necessity from P to R. Here's an example of hypothetical syllogism. From the fact that Rex is a dog, we know he's a mammal. From the fact that Rex is a mammal, we know he is warm-blooded. So we conclude from the fact that Rex is a dog, we know he is warm-blooded. At this point, it's worth stopping and seeing how biconditionals fare with these argument forms. First, we will look at a biconditional where one of the component propositions is stated. We have P if and only if Q using our P's, AR, and Q ball. We state one of the component propositions. We infer the other. Pretty simple. Since it's a biconditional, it does not matter which proposition you state since each is sufficient for the other. In this way, we have kind of a modus ponens using biconditionals. Modus tollens works the same way. We start with our biconditional. Next, we give the denial of one of the component propositions. Finally, we infer the denial of the other. Since the propositions are necessary for each other, it does not matter which proposition you deny. You can infer the denial of the other. Let us look at comparing equivalent propositions. First, let us simply state that P is equivalent to Q. Okay, no big deal, nothing we haven't seen so far. Let's add another equivalent statement. Let's say that Q is equivalent to R. Okay, two equivalent statements that share a component proposition, namely Q. What do you think? Is there a truth relationship between P and R? Yes, there is. P is equivalent to R. Remember, P is sufficient for Q, Q is sufficient for R, so P must be sufficient for R. It also works for necessity from P to R. So P is sufficient and necessary for R. Thus, they are equivalent. The form is pretty straightforward. It looks a lot like hypothetical syllogism using conditionals. First we have P if and only if Q. Next we have Q if and only if R. So we infer P if and only if R. Okay, nothing very surprising when dealing with a biconditional that expresses equivalence. One wonders what happens when you use a biconditional expressing contradiction. Well, let's take a look. First, we assert a biconditional expressing contradiction. We have our P's, our double arrow, our cue ball, and a not over the cue ball to represent P if and only if not Q. Next, we state one of the component propositions. Finally, we infer the other component proposition. Okay, no surprise here. Had we stated not Q, we would have inferred P. Well, let's change things up a bit. Let's start with our biconditional expressing contradiction like before. Okay, let's deny P. Okay, what happens next? Can we infer anything? If so, what? Remember, the biconditional states that P and Q have opposite truth values. If we say that P is false, what can we conclude about Q? Since P and Q have opposite truth values and P is false, we know that Q is true. So we have our conclusion. Earlier, we saw that when P is equivalent to Q and Q is equivalent to R, P is equivalent to R. Well, what happens with contradiction? Okay, first we state that P is contradictory to Q. Next, we state that Q is contradictory to R. What do you think? Is P contradictory to R? Pause the video now and think it through. Okay, you've thought it through for some time, I hope. P and Q have opposite truth values. Q and R have opposite truth values. Does this mean that P and R have opposite truth values? Well, suppose P is true. What is Q's truth value? If P is true and P and Q are contradictory, then Q is false. Q is contradictory to R, and Q is false, so R is true. P and R match. Well, what happens when P is false? Well, if P is false, then Q is true. If Q is true, then R is false. Well, P and R match again. I figure some of you might have thought that since P is I figured some of you might have thought that P would be contradictory to R. In fact, P is equivalent to R and if both are contradictory to Q. It might be more clear when you look at the following slide. First, we state that P is contradictory to Q. Next, we state that Q is contradictory to R. We infer then that P is equivalent to R. Surprise, surprise. Well, here's another twist. If P and R are contradictory to Q, and if P and R are contrary to one another, then Q must be true, and P and R are false. I'll let you figure out how. Okay, here are the terms for this video. You should know these arguments off the top of your head and be able to use them in their various permutations. Alright, that wraps it up for simple argument forms. The next video deals with complex argument forms. Complex argument forms are arguments composed of simple arguments. They're really fun. Complex argument forms are also very powerful.